Hello everyone. Today's video is about Gaussian elimination. What Gaussian elimination is a procedure to systematically find the reduced row echelon form of a matrix in order to solve a linear system of equations. We'll explore what Gaussian elimination is by help of this example up here. Here's a linear system. There's 5 variables, x1, x2, x3, x4, and x5. And there's 4 equations. To solve this linear system, the first step that we want to take is to convert the equations into the formalism of an augmented matrix. So let's write the matrix. This matrix has coefficients 0, 2, -1, 2, 1, 2 in the first row. The second row is 1, -2, 1, that's a minus, 2, 3, and 6. I'm reading off the coefficients from those equations. 2, 4, -3, 2, 0, 3. And the last one is -3, 6, 2, 0, 3, 9. Here's our augmented matrix of the form A with a vector B stuck next to it. Now we'll apply Gaussian elimination to this matrix. The first step in Gaussian elimination is to identify what's called a pivot column. The pivot column is the first leftmost non-zero column. In our case, it's this column up here, because it contains non-zero entries. The top position of the pivot column, which I circled now, is called the pivot position. Once we identify the pivot position, our next goal is to make sure that there is a row with a non-zero entry in the pivot position. So we have to find one of the rows in the pivot column, well, one of the rows, such that its pivot column entry is non-zero, and then move that to the pivot position. In this case here, if you look at the second row of the matrix, it has a non-zero entry in the pivot column. It's a 1. So we may use that row to swap it with the first row and put the non-zero entry in the pivot position. So after that's done, what I did here was to swap these two columns, these two rows. And now there is a non-zero entry in the pivot position. The reason why that's important is that the next step is to use the pivot position and the entry in it to eliminate all other entries in the pivot column. Before doing that, there's a step labeled 3a, which we won't have to do here. We need to make sure that the entry in the pivot position is a 1. In this case, it's already a 1. So step 3a does not affect this case. We can jump to step 3b of Gaussian elimination, which, as I mentioned, has as its goal that of eliminating all of the entries in the pivot column that aren't our pivot position. Let's try and see how to do that. Well, for example, here, to eliminate the entry 2, I will have to take the third row and subtract from it twice the first row. Let's do that in practice. That's what I've written here. To eliminate the 2 that was in this row, I will have to take that third row and subtract from it twice the first row. If we do that, the result is the following. Let me copy this row. when we take the row that I just pasted here, which was row 3, minus twice row 1, what we get is the following. We'll get a 0 here. Then we have 4 minus 2 times negative 2. So that becomes an 8. Then we have minus 3 minus 2 times 1. That's negative 5. Minus, we have 2 minus 2 by 2. So that becomes a negative 2. And the last ones are 0 minus 2 times 3. That's negative 6. And 3 minus 2 times 6. That's negative 9. I will do the same thing with the third row. This time, this third row has a negative 3 here, which means that if I take, sorry, the fourth row. The fourth row has a negative 3 here, which means that if I take 3 times the first and I add it to the third, I will get a 0 at that entry. And that's exactly what I want to say. I will take the fourth row and I will replace it by itself times 3 times the first row. I'll just write down the solution, but I encourage you to check that that's what you get when you take this fourth row and add 3 times the first. The numbers you get are the following. You get 0, 0, 5, 6, 12, and 27. So this is the conclusion of step 3b. We found a pivot position, we put a non-zero entry in it, we made the non-zero entry equal to 1, and then we eliminated all the other entries in that column. The next step is to repeat the process, starting this time with a smaller matrix. So the new pivot column will be the next one, the next column with non-zero entries. In our case, the second column will be the new one, and the new pivot position will be the top position under the previous pivot. In other words, the new pivot position will be this number 2. Let's repeat the process with that. Since I have a number 2 there, I want that to be my pivot entry. Therefore, I need to divide that row by 2. So I will replace R2 with R2 divided by 2. When I divide it by 2, I get 1 here, minus 1/2 here, 1, 1/2, and 1. So now my second pivot is an entry 1. What I need to do next is eliminate all of the non-zero variables in the column corresponding to the second pivot. To do that, I'm doing the following thing. To eliminate the minus 2, I will have to replace my first row with itself plus twice the second row. To eliminate the 8, I will have to take my third row minus 8 times the second row that I'm using. Let's compute these. First, I like to write down the second row, which is not going to change, and it will be unaffected by this process. And I'll also write down the fourth row because nothing is going to happen to it at this step. Okay, now let's eliminate entries in the first one. Nothing changes there, and this becomes a 0. Here I have 1 plus 2 times 1/2, so that becomes a 0. Here I have a 2 plus 1 times 2, it becomes a 4. That's a 3 plus 1 is 4, and 6 plus 1 becomes 8. Let's do a similar process with the third row. We have zeros here, and we have a 0 here because that's how we set things up. Here we have minus 5 minus 8 times minus 1/2, which is minus 5 plus 4, which becomes a -1. Here we have a -2 minus 8 times 1. That's a -10. In the next, you also get a -10. That's -6 minus 8 times 1/2. -10. The last one is -9 minus 8 times 1 becomes -17. Okay, you see now that the second step is completed because we currently have 2 pivot columns that are completely clean. They only have a leading entry in the pivot position and nothing else. So our next goal would be to focus on this other submatrix down here and consider our third pivot column. There's non-zero entries in there. In particular, the pivot position is this entry right here. Now, the next step is to make the entry in the pivot position a 1. The way that I can turn a -1 into a 1 is by, and I'll write it here, replacing my third row with minus itself. In other words, I am free to change the signs to every entry in the row. I'll do that so that my leading entries is equal to 1 now. The effect of that is that I have now my pivot entry, which is correctly equal to 1, and I can keep on working with the goal of eliminating all of the other entries in that column. There they are. So maybe let me just copy the matrix and we'll manipulate what we need. So we'll look at these 2 rows. To eliminate the -1/2, it suffices for me to replace the second row with itself, to which I add the third row divided by 2. Because then I would get -1/2 plus 1, sorry, -1/2 plus 1/2. To eliminate the 5 in the last row, I'll take the last row, R4, and then I will subtract 5, the third row. And I'll put that in place of the 4th row. Okay, let's compute this. Nothing is changed here because the third row is 0 there. This becomes a 0 by construction. What else is there? We have 10 plus, sorry, we have 1 plus 10 divided by 2, that's 6. Then we have 1/2 plus 10 divided by 2, that becomes 11/2. Then we have 1 plus 17 divided by 2, and I will just leave that as indicated by 19/2. Let's do the same with the last row. The first 3 entries will be zeros because that's how we set things up. Here we have 6 minus 5 multiplied by 10. That's -44. Then we have 12 minus 5 multiplied by 10. That's -38. And then we have 27. I'll write this out. 27 minus 5 times 17. And that's 27 minus 85, which should be, well, let's see, 58, minus 58. Okay, so this last row now has a 0 in the third column. So the third column is completed, and we're almost done with our process. The last thing that we need to do is to, well, there's one more step. What we need to do next is to do the same process for the last row, which means, move this a little bit, we want to take our last row, R4, and divide it by -44, so as to get a 1 here. When I do that, I'll get the following numbers. I'll get a 1 there, and then I have, maybe I'll write them out. It was a -38 over -44. That becomes 19 over 22. And then the last one was, so that's the number that we have there. Here we have -58 over 44. 58 divided by 2 is a 29 over 22. And maybe, yeah. Okay. Oops, that's a plus then. There we go. Okay, we're almost home, meaning that we now have our 4th pivot entry. However, what we still have to do is to eliminate all of the entries in the pivot column corresponding to the 4th pivot entry. So what are we going to do? How are we going to do that? Is as follows. This time I will maybe not compute all the numbers, but I'll tell you what to do. So, for example, the way we fix the first row is by replacing it by row 1 minus 4 times the 4th row. Because there's a 4 in row 1, and we want to multiply 1 by -4 so that they add up to 0. The second row will be fixed as follows. You can just obtain it by subtracting 6 times the 4th row. And the third row is obtained by taking itself minus 10 times the 4th row. Now, if you do these computations, let's do the first one. We'll have 0 here. We'll have a 0 here because of how we set things up, because we'll have 1 minus 4 times 1, and that's a 0. The entry here will be 4 minus 4 times 19 over 22. If we compute this, the result you get is, well, we can just do it. This becomes an 11, this is a 2, so we get 44 minus 38 divided by 11, and that is did I do anything wrong? No, that seems fine. That should be a 6 over 11. Let's compute the other entry. Up here, what we get is, well, entry 1 has an 8 there, minus 4 times 29 over 22. When we compute this, we get 88 minus 58, which should be a 30 over 11. The other numbers that come out of this should be, if I didn't make any mistakes, minus 107 over 11 and minus 19 over 11, minus 15 over 11, and minus 42 over 11. Okay, at this point, Gaussian elimination has terminated. We have 4 pivot and 4 columns, which only have leading entries 1 and then nothing else in them. So we are now left with the interpretation of the result. And we can do it as follows. I will just write it here. Let's have a look at that matrix. So, and every row of this matrix will correspond to an equation in our linear system. I'll write the first row, that's x1 plus 6 over 11 x5 equals 30 over 11. x2 minus 107 over 11 x5 is equal to minus 19 over 11. x3 minus 15 11 times x5 is equal to negative 42 over 11. And x4 plus 19 over 22 is equal to 29 over 22. 19 over 22 times x5. Sorry. One other feature of this matrix is that the column x5, the column corresponding to x5 is not a pivot column, which we can interpret as x5 being a free variable. And in fact, you can see that x5 is free in all of the equations that we just wrote. If I modify these equations as follows, moving x5s to the other side. So I could rewrite this equation as x1 equals minus 6 over 11 x5 plus 30 over 11. x2 will become 107 over 11 x5 minus 19 over 11. x3 will become 15 over 11 x5 minus 42 over 11. And x4 will become minus 19 over 22 plus 29 over 22. If I manipulate these like this, then I can condense this writing into just one expression for the general solution using vectors, where I have, a vector of constants, which are the constant terms appearing here in these side of equations, and a vector of coefficients of my x5, which are the numbers appearing here. Okay, that was Gaussian elimination, and that was our first example of it.